Bismillahirrahmanirrahim. Assalamu alaikum, dear students. In the previous lectures, prior to this week, we studied different metallic structures. When we draw crystalline structure, it becomes necessary we need to specify a particular point within a unit cell, or we need to draw a crystallographic direction or a crystallographic plane of atoms. We specify all these crystallographic coordinates by following already developed labeling conventions, as they are said. In this and next lecture of this week, we will study to draw and designate coordinates for crystallographic points, directions, and planes, respectively. So, let us begin. Okay, crystallographic points, directions, and planes. Points will refer to a certain point or location that we want to specify within the crystal structure. Direction will be just like we develop directions in vectors in mechanical calculations. Direction will refer to position with reference to a certain axis or center of axis, and plane will define the orientation of certain arrangements with respect to the axis center. For all these, labeling conventions have been developed to specify respectively these points, directions, and planes of atoms for the crystallographic structures. These labeling conventions use three numbers or indices, as they are called, to designate or inform us about the location of point or direction and a plane. These indices are determined on the base of unit cell. Reference is unit cell with right-handed coordinate system consisting of three axes, x, y, and z, and that's situated at one of the corners of the unit cell and coincide with unit cell edge lengths, as you can see in figure 3.4. It means just like three-dimensional space coordinates, if you have x, y, and z axis, you will locate these axes so that x-axis comes or coincides with one edge of the cube or the cell, and y-axis just lies over and parallel to another edge of the cube, and similarly z-axis gets in parallel or coincides with yet another edge of the cube. So three mutually perpendicular axes. Actually, this is not a condition that every time in every crystal structure they are perpendicular, but specifically for cubic crystalline structures they are perpendicular. So you locate x, y, and z axis along the edge lengths of the cube. Unit cell is, keep in mind, the basis for determining these indices, and we develop a right-handed coordinate system that consists of three axes with center at the corner and that coincides with the unit cell edge lengths. Now we go on to determine point, direction and plane coordinates using this reference coordinate system. Point coordinates. You see here in the figure 3.6 shown in the right bottom corner of the slide that there is a cube and its edge lengths are A, B and C along X, Y and Z axis respectively, and there is a point P located at a certain position within the cube. We need to determine the coordinates of this point P. As we said earlier that we use three coordinates or indices to specify position of a point within a unit cell. So these indices can be a whole edge length or a fraction multiple of this one unit edge length. Just like you have been doing or drawing vectors in vector mechanics or dynamics, you need to start from the center and move along x-axis, then along y-axis and then along z-axis, and in the process you will see, you will keep in mind that if edge length is A for x-axis, B for y-axis and C for z-axis or z-axis, so what is the total length of this point or the movement that you started from the reference axis, I mean 0 coordinate, and moving along x-axis, how long it is. So this will give you edge length along x-axis, and then you move along y-axis and you multiply this fractional distance with the total edge length to get location of this point, and then similarly you move along z-axis and multiply with edge length to get the distance along z-axis, and these 3 points given by QRS give you the point coordinates or the location of the point for this cubic unit cell. Okay, this is our method to determine point coordinates for a cubic unit cell which has edge lengths of A, B and C along x, y and z coordinates respectively. This is simple and straightforward. You have been doing this already. To make it more clear, in the next slide we take into account some more examples. Okay, here we have a cube and we designate different point locations. Maybe these point locations coincide with the atom positions for this unit cell. Anyways, for example, take point 1. What are the coordinates for this point, if we have taken our x, y and z axis coordinate with the center lying at this corner, then you can see very clearly that this point 1 is at the center of axis. So its coordinates will be 0 along x-axis, 0 along y-axis, 0 along z-axis. If we take some other point, for example, take point 8. What will be the coordinates of point 8? Of course, you first have to move along x-axis one whole edge length, then along y-axis one whole edge length, and then along z-axis one whole edge length. So what will be the point coordinates for point 8? Take for example point 3. Okay, now just opposite to you in the front face of the cube, point 3. What will be the coordinates of point 3? You again start from the origin that you have taken at point 1, 0, 0, 0 coordinates. You first move along x-axis. One whole edge length you have to move. And then to reach point 3, you need to move along y-axis. One whole edge length along y-axis. Do you need to go along z-axis? No, we are already our point location. So one whole edge length along x-axis, one whole edge length along y-axis, and we reach our point. So what will be the coordinates for this point 3? I hope you can easily draw point coordinates for point 3 and similarly for all other points given in this cube. Look at point 5. Can you agree yourself with the coordinates written for point 5, that is half of x-axis, half of y-axis and half of z-axis? Please just convince yourself of these coordinates by drawing these coordinates yourself. You move along x-axis, then along y-axis and then along z-axis. Okay, we move on to the next. Next is how we draw direction coordinates, or how we determine direction coordinates. Okay, crystallographic direction is a straight line, or you can say like a vector between 2 points, starting point from the origin and terminating at the end point that we have fixed for ourselves. I hope you will remember displacement vector, for example. What is this displacement vector? You start from origin and a direct line to the head of the final position vector. You draw a straight vector and that you call as displacement vector. Somehow, some sort of analogy exists. Here you will draw a direction vector that starts from origin and terminates at the end location. The detailed procedure, and of course at that end point you will draw the coordinates for that direction vector, just like we have been drawing these coordinates are indices for point locations. Procedure to draw crystallographic direction is simply reproduced here from our textbook, and it details how you will need to draw position coordinates for a certain position that you have fixed in crystal structure for yourself. That you have a starting point for which the coordinates will be 0 0 0 or some other location that has another coordinates, and then you go on to the final point and then draw coordinates for that point, and then simply subtraction gives you the coordinates that are then determined for the crystallographic direction. Anyways, there are some procedural steps that you need to keep in mind when you are drawing direction and in the next plane coordinates. As is procedure given for direction coordinates, in the beginning procedure is analogous or similar to that you use to reach at a point in a unit cell. Of course, for this you are free to choose right-handed x, y and z coordinate systems whose origin anyways coincides with unit cell corners. The process of locating point in unit cell or finding component vector along xyz direction of the direction vector are other alternative ways to determine direction coordinates in addition to this standard procedures that are reproduced in slide 5. What is required? That when you have drawn the point coordinates for initial and final position, and then you just draw the vector coordinates by subtraction, you then need to reduce these coordinates to smallest integers. I mean, these coordinates must be in integer values, and then you do this by multiplying with common factor, and you put indices in square brackets without commas. Okay, in point coordinates you just write 3 point coordinates. In direction coordinates you determine coordinates as per the point coordinates, and then you reduce them to lowest integral values, put these 3 indices together without commas, and you put square brackets around these coordinates. So this is a bit of difference that you need to keep in mind when drawing direction coordinates. For example, here you have a cube with edge length with edges with a coordinate system x, y, and z, and if you have u, v, and w, the direction indices along x, y, and z axis, then as per the procedure given in the previous slide, these indices u, v, and w can be found by using the following relations given in 3.10a to 3.10c. N is the factor that reduces indices to lowest values. This n could be any number that is able to reduce these coordinates into lowest integers. of course, that you will select as per the coordinates denominator of the coordinates. So again, you need to use, for example, u is along x-axis. Of course, you take start from the origin and then you go to the final point. Final point is x2, initial point is x1. X1 has 0 0 0 coordinates and x2 has is just along x-axis. So you have point coordinates at x2 along x-axis, the edge length, the, the corner just in front of in opposite to you in this figure shown on slide 6, right bottom corner is 1 and y and z are 0. So it is 0 0 0 at the origin, 1 0 0 at the cube corner along x-axis opposite to you. So what are the then direction coordinates? It is x2 minus x1, that is 1 minus 0, and the other two are 0 0 already. Okay, and you divide by edge length, and that is a or 1, whatever you say, and it's 1 0 0. It's already in reduced form. There is no denominator to reduce to integral values. So n is again 1 here, and this reduces your position coordinates along x-axis as 1 0 0. Similarly, you can do this for other two coordinates along y and z axis, and you can determine position coordinates for a direction coordinates for a certain direction. Two other direction coordinates are given, that is 1 1 0 shown for blue arrow and 1 1 1 shown for another reddish arrow. Please try to convince yourself of these coordinates, and if you have any confusion, we of course will be discussing this during our online session. Okay, we move on to the next. We have been drawing point and direction coordinates. Most of the time we find vector components of direction vector resolved obtained by resolution of direction vector along each of x, y and z axis, and if then required, we reduce this to smallest integer by common factor. Okay, there is a family of directions. What this means? Family of directions refers to the same atoms in the same positions. If you find a longer direction, the same number of atoms are present at same positions, you call these directions as family of directions. I mean, these directions are similar to each other. They may be pointing to different positions. If you see with respect to the vector directions or their drawings, you will see that they are, one is from towards y-axis, one is towards x-axis, but as long as these directions involve same atoms in the same positions along any cube edge length or within cube, these directions are referred to as family of directions, and they are called equivalent directions. These are called crystallographically equivalent directions. They are not vectorially equivalent directions. Do not confuse this with the vectors or equivalent vectors. These directions are crystallographically equivalent directions because they point towards same positions and involve same atoms. Same means same number of atoms along same positions, at the same positions. If you look at, for example, if you look this cube with different directions drawn on it, you can easily recognize or convince yourself that all these vectors point or involve almost similar same to atoms and that are located at the same positions. I mean, if you just turn around this cube, if the right side face comes in front of you, you cannot recognize that this was the side before it was on the right side and now it is in front of me. This is the same. So you cannot distinguish between two faces, front face that is now in front of you and the right face or the upper face. I mean, if you just rotate at 90 degree with this cube, the vectors will again be the same. They will again same involve the same two atoms at the same two positions, and you cannot distinguish that this was the side before turning at 90, it was on the left side or the right side. So these directions are called crystallographically equivalent directions. So these equivalent directions actually means that the spacing of atoms along each direction is the same, and it remains the same if you simply give it a turn. All the directions represented by direction vectors on the accompanied cubic crystal are equivalent as shown in front of you on this figure. Equivalent directions are grouped together into a family represented in angle brackets, like for example shown on this slide. 0, 1, 1 is family of equivalent directions that consists of 0, 1, 1, 0, 1, minus 1. Okay, you can also put minus 1 on the head of 1, just like we put a vector arrow, and 0, minus 1, 1, 1, 0, 1. Okay, these are the family of direction. This concept is of course applicable to other crystal systems as well. It's just not for cubic crystals. Okay, with this we finish our 2 days lecture about first lecture about directions and points, and we will be considering plane coordinates in the next lecture. Assalamu alaikum.